and welcome to this video about electric power. We're going to look at how to calculate electric power, how we calculate the cost of electrical energy, and how power companies transfer electrical energy. So remember, last semester we learned that power is the rate that work is done. And we can write that equation like this: power equals work per change in time. We can also write that as change in potential energy over change in time. When we talk about electric power, we are talking about the rate that charge carriers do work. You'll remember from previous sections that we can look at potential energy when we're talking about electricity via this equation. Change in potential equals potential energy over the charge. If we simply rewrite the equation in terms of potential energy, we get potential energy being equal to charge times potential difference. And if we substitute that into our equation for power up here, we can say that for electrical power, power is equal to the charge times potential difference over delta T. We also know that the rate of charge per time, this part of the equation right here, is defined as current. So we get an equation, power is equal to current times the potential difference. And here we have that equation written in a much neater form. Power equals the electric power equals current times the potential difference. The SI unit for power, remember, is the watt, capital W abbreviated. We can also plug in different equations, and I won't go through the derivation of these. It's pretty simple. If we just look at the equations we already have and that we already know, we can also write the equations for power using different terms if we need to. These are very useful. Power can equal current squared times resistance. Power can also equal the change in the potential difference squared divided by the resistance. I'm going to write down what I know. I know the potential difference is 120 volts. I know the power, it's been given to me in the problem, and I would like to find the resistance. That's my unknown variable. I'm going to choose an appropriate equation. I'm going to choose power equals the potential difference squared divided by the resistance. And then I can simply plug values in and solve for the resistance. And when I do that, I get my resistance equal to 10.9 ohms. So how do electric companies measure the energy consumed? Well, they use something called kilowatt hours, abbreviated lowercase k for kilowatt is capital W and hours is a lowercase h. 1 kilowatt hour is the energy that's delivered in 1 hour at the constant rate of 1 kilowatt. It has the equivalent value of 3.6 times 10 to the 6th joules. Joules is energy that has all been converted into watts and seconds, whereas a kilowatt hour is not in watts and seconds, it's in kilowatts and hours. So let's do a sample problem. How much does it cost to operate a 100-watt light bulb for 24 hours if the electrical energy costs 8 cents per kilowatt hour? I'm going to write down what I know. I know the cost of energy. I know the power is 100 watts. I'm going to convert that into kilowatts. And I know my change in time is 24 hours. I'm going to leave that in hours. Remember, I know that power is equal to the energy per time. Just remembering that equation, I can then rearrange this to solve for the amount of energy that's being used. And if I do that, I can simply plug in my values for power and time. And I can solve that and get a value of 2.4 kilowatt hours of energy. So I want my energy measured in kilowatt hours so that now I can calculate how much it costs. Remember, my cost of energy up here is 8 cents per kilowatt hour. So if I'm using 2.4 kilowatt hours of energy, I can multiply that by my conversion factor, the 8 cents per 1 kilowatt hour. My kilowatt hours cancel out, and I get a cost of a whopping 19 cents. So you've all seen signs that say danger, high voltage. You know that power lines, when they carry electrical energy, they carry it at very high voltages, very high potential differences. Why do power companies transfer electrical energy at such high potential differences? Basically, the answer is to minimize power loss, the I squared R loss. You remember power equals I squared R, or the current squared times the resistance. You know that wires usually have pretty little resistance, but if they are traveling over really long distances, resistance is proportional to length. And so over these very long distances, this resistance does come into play as a factor. Also, you can see that current is squared in this equation. So even more important than the resistance, this current really needs to be reduced to minimize power loss when transporting the electrical energy. So you also are familiar with this equation for power, current times potential difference. So we can transfer the same amount of power at really high currents and low potential differences, or at low currents and high potential differences. So that's what the electrical company does, is the power company transfers at very high voltages and very low currents over these long distances in the power lines. Then once that electrical energy gets to a city or some other central location, a transformer will reduce the voltage to about 4,000 volts, and then another transformer will reduce that again to your home to that familiar 120 volts that you're so accustomed to using. If you're interested in advanced ideas, try the conceptual challenges in your book, or maybe you have some other questions about anything at all, some area of interest from any topic in this video. I look forward to seeing what you come up with, and we'll see you in class.